Hello, and welcome to the lesson on sequence of transformations. So this is a continuation of the previous lesson where we were looking at how one geometric object moved from one place to another using a rotation, reflection, translation, or dilation. Now we're talking about a sequence of transformations. We're talking about multiple things happening, like a rotation and then a dilation, something like that. Did you know that cartoons on TVs use transformations much in the same way as video games? So, like, you don't want to have to redraw the same thing over and over and over again. So, what they'll a lot of times do is they'll copy, paste, and perform a transformation to make a new image. So, even with just one image, so this little cartoon strip I have down here, I made that with one image of whatever that kid's name is from Fairly Odd Parents, Jimmy, I think. So, I made one image of him and then this little brick wall thing. That's it. So it's one image and some transformations. So it looks like he's running, he rotates, and he runs up the wall, he rotates again, and he falls. So that has a translation, rotation, dilation. I did not get a reflection in there, where he would like face the other way, just because I only have so many spots to put them. But I mean, that's enough of a little cartoon. You can kind of make sense of what's going on. As I said, in the last lesson, we had like 8 vocabulary words. Now there's none. There won't be any for a while. So we're just going to reuse those same words. So let's get to it. So it says, in each figure, describe the transformations that exhibit congruence or similarity between them. Now what that means, that those directions are confusing for some students. So describe the transformations that shows that either these two shapes are congruent, they're identical, these are not identical, these are. So show the transformations that shows that these are identical, or that shows that they're similar, like this one here. So what we want to do is just basically list out the transformations like we have been doing. So what I recommend, my letter A, I'm looking at that and I'm going to go for like the obvious answers first. I want like the basic answer. What things are happening in this transformations? The very first one that I see, the obvious one that pops out to me, is a dilation. A dilation happened. I can tell because they're different sizes. And the next thing that looks like that happened to me is a translation. That is the move or the slide, because I'm imagining if this dude gets bigger, bloop, he's really big now, I'd still have to move him into the right position so that everything be lined up. Okay, that is your basic answer. That's enough to just identify, but we want to do better than basic. We want to get a better or the best answer later. So let's see here. Dilation, how? Well, I know this is the original because it's ABC. This is the Newman because the image, pre-image, image, because of this little prime guy, this little guy right here in the corner. That tells me that this is the new. So it's going from this one to that one. And maybe draw that little arrow if it helps you out. Like I can tell in this one, it's going from this to that. Okay? So dilation, how? That was loud. Oops. I just restarted my computer because it was acting funky. Now all these things are popping up as the computer's still turning on. Sorry. So dilation, how? Well, this side is 2 boxes long. I'm using this side because it's easy to count. I'm not going to pick this side because why? I'd have to do Pythagorean Theorem to figure out how big this is. But I can figure this. This is 2. On the new guy, it's 4. How many times bigger is that? Well, that would be 2 times bigger. 2 times 2 is 4. So it's a dilation with scale factor of 2. It's 2 times bigger. Now, the next thing we need to know is, where's the center of that dilation? Where are we dilating from? Most of the time, if you have a choice, I would pick one of the corners of the object. So, I'm going to, oh man. Okay, so I've got my object. I need to erase this arrow, else he's going to get zoomed into. All right, if I take this and I zoom it, I personally, I would pick this corner right here. And watch what happens. I'm going to put my thumb right there, my other finger kind of out here somewhere, and then I'm going to zoom out. I'm going to try to keep my thumb on that spot. I'm going to try to keep that corner in place. That's as much as lets me do it. Now, that is actually 2 times bigger. So I just dilated it from that point right there. Notice how that point didn't move. I used this as the center of dilation. Everything got zoomed in and out of that point. And then what we can do is when we're going to translate now, all I'd say is, oh, okay, so now this guy, I'd move him over there. You see how they exactly line up? But I didn't have to pick point C. I could have said, oh, let's dilate from point A. And that's actually going to change our translation. Because now to move this down here, it's different. Or I could have said, oh, let's dilate from point E. Or point B, I'm sorry. Point B up there. Now, this translation is going to be different. So there's a variety of actually different answers you could have said. Just like, and I don't know, we're not even done with the problem. I'm going to stop rambling here in a second. But you could have said, oh, let's do the translation first. Let's move this point C over here and then dilate with a scale factor of 2. It's still those two operations happening, a dilation and a translation, but there's a lot of variety and decision and choices that you can make along the way. So we're going to have maybe slightly different answers throughout this lesson. All right, off my soapbox, back to it. So I'm keeping this. So I'm going to dilate with a scale factor of 2 about point C. I'm going to use that because, well, it already has a name. If it didn't have a name, I would say about point 1, 2, 3, 4, 5, 6, 7, comma 1. And now, you know what? Maybe 7, comma 1. It's still point C. It's just a little better. So now we have the perfect dilation. Everybody in the world can follow this. So they took this, they dilated with a scale factor of 2. It's 2 times as big from that point. Now, translation. Translate how? Well, we're going to translate this. I'm going to translate this point here down to this point here. C to C. And my translation, I can see, is down and left. Down how much? Looks like it's down 3. 1, 2, 3. And then left 1, 2, 3, 4, 5. And so that was the good and the better. Now the best. Using the rule x comma y. So what happens to the x values? Well, as you're moving to the left, your x coordinates are getting smaller. So your x value is going down by 5. It moved left 5, the x number went down by 5. As your y values, your y coordinates, are going down by 3. So minus 3. There is the perfect translation, or the perfect description for the translation now. So now everybody in the entire world could follow this exact thing and get from this original pre-image of ABC and get to our new A prime, B prime, C prime. Okay? Letter B. Let's see if we can zoom in a little bit here. All right, so that's what we got. So take a second and look. You don't have to write just yet, but look, what types of operations are happening? What sequence do you see? I see a rotation and I'm not quite sure what's going on after that. I'm not quite sure what the second operation is, but I definitely see a rotation. So I'm going to start with that, actually. Sometimes you may not be sure what the second operation is. It's not as obvious. I mean, depending where I rotate this from, I might be able to get this to land up exactly with that. Might be hard to do, but I might be able to do it. But I'm not going to focus so much on that. I'm just going to make a rotation, and then I'll figure out what's going on, and then get it to the second guy. So rotation, how? Well, it's going to be a rotation of 90 degrees. And I can tell because it looks like, remember, this was the original. If I would take this guy and spin it up like this. So I'm imagining right now it's laying on its side. Here is its side. And when you turn it, here is its side. So it's kind of like being like sat up. That's a 90-degree rotation. Okay, 90 degrees which way? Is it going the way a clock spins or counterclockwise? Well, this one is being rotated, as my little arrow shows, is being rotated clockwise. So it's a rotation of 90 degrees clockwise. This is the good, this is the better. Let's get the best. Where are we rotating from? Are we rotating from the origin? From point X, point Y, some other point? You got to pick one. And again, a lot of times, I personally would pick either X or Y. Because rotating from the origin is not actually that very easy. Not here. But rotating from a point is very easy because you know one thing. You know that point is not going to move. So if I rotate this from point X, I need to redraw that a little bit. Give myself a little bit more space. There we go. Fat fingers and all. So if I rotate from point X, I know point X is not going to move. I'm going to try to keep this all perfect. So point X stays the same. Rotate 90 degrees. That was pretty darn close. So point X didn't change. Or if we rotate from point Y, I'm going to put a finger on Y and try not to move it, and everything else rotates 90 degrees. Boom. Point Y didn't change. But in both those cases, look, this looks like that. It just needs to be translated, is the other one, translation. It needs to be translated up here. But if we picked something like the origin, which still does work, it would look like that. But a lot of students have trouble translating around the origin. If you don't, by all means, do it. It's the same number of steps. It's just maybe a little bit harder. Okay? So I'm going to rotate around point X. So I would rotate a rotation of 90 degrees clockwise about point X. So I'm going to actually perform that operation again so that we can get into the next step. So it looks like that. Now, the next step is, well, how do we get it to go from this to this? Well, that's that translation. Translation how? Well, it's definitely going up. Is it going left or right at all? Actually, no. Look, X to X. It's straight up. So up, how many? Up 1, 2, 3, 4, 5, 6, 7. Up 7. Good, better, best would be with the rule. Okay, the rule. X comma Y goes to. So what's happening with our X values? Are our X values changing? Am I going left and right at all? No. So actually, X stays the same. We don't have to do like a plus 0 minus 0. That doesn't do anything. So we just say, oh, X stays X. The X coordinates of each of these points stay the same. But the Y coordinates will go up 7. So my Y coordinates will go up by 7. And there we have it. So this is a sequence of transformations, 2 different transformations that you can then use to make one thing turn into the other. All right. Here's one for you to try. Now, this is a little bit funky. I'm gonna give yourself a little bit of time first. If you get stuck really quickly, like before you even know what to do, hit play and I'll give you a hint or two. So go ahead and try it first. All right, if you're stuck and you're like, I have no clue, this shape doesn't do anything for me. Something you can do is imagine a big old box around this. So imagine now it's kind of like a rectangle. I mean, point B touches this line here, point A touches this line here. Imagine that rectangle versus that rectangle. Now you can at least see the height and the width and the stuff to start to get some ideas down. Okay, so go ahead and try some more if you need to. Everybody else, here we go. So, things that happen. Definitely a dilation. Let's try that again. Dilation. And then either a rotation or a reflection. It's going to be a rotation, I can see. And again, you could have done this in a different order. Maybe you saw the rotation first and then the dilation, but it has to be these two. There's no other thing it could be. It had to be these two. Now, dilation of how much? Well, this is your original. This is your pre-image. And your pre-image is 1, 2, 3, 4 boxes wide. Your lightning bolt is 4 boxes wide. Your image, the new guy, is only 2 boxes wide. So how many times bigger is that? It was 4. It's now 2. That is half as big. You would multiply by 1/2 to get there. So it's a dilation with scale factor of 1/2. And where would you use the center of dilation? Honestly, I would pick point O. Do you see how these guys are connected at point O? So I would use that because I'm going to rotate around that point. I'm going to dilate from that point. That way that corner right there doesn't have to change. About point O. Okay. That is our dilation. So now we took this lightning bolt and we shrunk him. He now looks like that, sort of. Okay, I can't actually shrink the lightning bolt, but I can shrink the rectangle around him, so it looks like that. Now we need to do that rotation. So we're going to take this guy and we're going to spin him halfway around the circle. So that is a rotation of 180 degrees. That's halfway around a circle. Vroom. We don't need to say clockwise or counterclockwise because halfway around is the same as the other halfway around. It's the same both ways. So a rotation of 180 degrees. About point O. And there we have it. So again, you may have this in a different order, but in this problem, it actually had to be these exact same two things. You had to dilate with a scale factor of 1/2. You had to rotate 180 degrees. The rotation had to be about, no, I guess it didn't. If you dilated, say, like about point A, that's going to change your rotation. You might even add a third thing in there. You might have to like dilate around this point and then translate a little bit and then rotate, and it gets pretty funky. So it's beneficial if you take your time and think about where would be the easiest place to dilate from, to rotate from. If your objects share a point, it's that point. A little summarizing thinking question. How can you tell, after a sequence of transformations, if two shapes are similar or congruent? I want you to pause, I want you to think, I want you to put down an answer. Well, you can tell if they are congruent. I'll pick that one first. If they are, I'm going to say if they're equal, if they're the same. In the other lesson, I was using the word twinsies, if they're twins. So they should be twins. Same size, same shape, same everything. One might be facing the other direction or turned or something, but they are the same. They should be similar if they're the same size but a different, same shape but a different size. So if one is just proportionally larger than the other, one is like, is bigger than the other. Okay, so if one is bigger than the other, that's when they're similar. And that came through a dilation. Dilation is the only thing that makes similar figures. So in this problem, they want us to draw the required transformation. So we have this, and they want us to draw a transformation. Be sure to label your points. Okay, so reflect triangle ABC across the x-axis, then dilate it with a scale factor of 2 about point A. So this is almost like, this is the reverse of what we were just doing. Before, they would give us the before and the after, and then we would come up with a description. Here is the description, and we need to be able to draw the before and the after. And I'm curious, if you'd like to take a little bit of time and see how far you can go with this on your own before you even do it once, try it. I'm going to get started here in just a second. Okay, second's done. How to get a drink. So, first things first, we're going to do that. We're going to reflect this across the x-axis. And make sure you know which one is the x-axis. X, Y. So you are not reflecting this way. No, no, no. We're reflecting this way. And to do a reflection, to make it work out right, they need to be a mirror image across this line. So the distances have to be exactly the same. So like, see how this is 3 boxes down from x? So if I go 1, 2, 3 boxes up from x, that's the new home of point B. The C is 5 boxes down. It's the 3 plus 2 more. So 3 plus 2 more, that's the new home for point C. And you know what I'm going to do? Here, I'm going to use my highlighter. Oh my goodness, he's big. So there's B, there's C. And I'm using my highlighter tool because this is not my final answer. This is just an in-between step. There. That is a reflection across this line. And you notice I did A. Once you have 1 or 2 points, you can kind of just recreate the image. I saw that A was, horizontally across from C to the right of C, and I just put it across. So now we have that. That's the first piece of the puzzle. We did the reflection. Now we're going to take this, it says, then dilate it with a scale factor of 2. So it's going to be 2 times as big. All the lengths are going to be 2 times as big about point A. And what that part tells me is point A is not going to move. So I'm going to put him in permanent blue. He is now my new or final A point. But these other points are not going to be here. I mean, if this is 2 times as big, it's going to be like out here or something. Well, let's count boxes. 1, 2, 3, 4, 5, 6. This is currently 6 boxes long. So if it's 2 times as big, it'll be 12 boxes. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right about there. That'll be the new home, the final home for point C. So I'm going to call it C prime. I'm going to draw the line in. Now, point B needs to be along the same line. Remember, if this triangle is just getting bigger, all the angles and stuff stay the same. So I could kind of just go like this and go, it's going to be here. I'm making the same line. I'm just making it kind of line up with C. That's one way of doing this. The other way is going, well, if this was 2 units before, and it's 2 times as big, it'll now be 4 units. 1, 2, 3, 4. And that is exactly the same line we had a second ago. And that is B prime. So there we have it. We've taken this shape. We have reflected across the x-axis, and then we dilate it with a scale factor of 2 about point A. Point A stayed the same. That wasn't too bad. Are these shapes similar or congruent? And how can you tell? Well, these shapes are not congruent because they're not twins. They're not exactly the same. They are similar. And how can I tell? I did a dilation. And dilations make similar figures. So that's a nice, pretty clear answer. I mean, a dilation happened. Dilations make similar figures. Boom. That's interesting. What is the ratio of the area of A prime, B prime, C prime to ABC? So, in case you forgot, ratio, a lot of times we write that as a fraction. So I'm going to do a fraction. So I want the ratio of the area of A prime, B prime, C prime over the area of A, B, C. So this is kind of like setting up my ratio. That's what I'm going to get. Those are the numbers I want to find. So, do you remember how to find the area of a triangle from back in, like, I don't know, 6th and 7th grade? This one's not on the 8th grade formula sheet. Area equals 1/2 the base times the height. Base is 6, height is 2. Calculator says 1/2, you know what? I'm just going to use 0.5. 1/2 times the base times the height is, this one has an area of 6. I'm going to throw that down in my formula. Area of ABC, I hate that little thing. Area of ABC we found was 6. Now, before we find the area of A prime, B prime, C prime, do you want to take a guess at what it is? If you said 12, I like where your brain's at. You're not right, but I like where your brain's at. You were thinking, hey, it's 2 times as big. The area is going to be 2 times as big. I like where your brain's at. Unfortunately, it doesn't quite work out for you. This side is 12 and this side is 4. So if I take my 1/2 times the base, 12, this is the flat side, times by the height, 4, it's not going to be 12. It's going to be 24. And you go, why the heck? Like, everything was 2 times as big. You're right. The sides are all 2 times as big. But if you made, this got 2 times as big and this got 2 times as big, your whole area is 4 times as big instead of being just 2 times. So there's the ratio of these. And we'd probably want to simplify. If you want to use your calculator, you can do that. Or you can do it in your head. It's going to be 6/1. I hate that. Oh, man. 24 fraction. See, wouldn't this just be much easier if you just did it in your head? It's going to be 6/1. Equals, 4/1. See? So the ratio is 4:1. This area is 4 times bigger than this area. That would be our ratio. Okay? So that one was for me, and we did most of it together. This one's for you. I would like you to try to do as much of this on your own as you can. So you're going to draw the required transformation. Be sure to label your points. So it says here trapezoid ABCD, ABCD is translated down 5 and right 5. Then ABCD was dilated with a scale factor of 1/2 about the origin. So could you please take your time and pause the video and do that sequence of transformations right now? When you're ready to continue, hit play, and we will go through it together. All right. So I'm going to do this translation in red, and then I'm going to do green's not good for me. I'm going to do this part in this pinkish magenta color. All right, so red. Trapezoid ABCD is translated down 5, right 5. Well, that's actually fairly easy. So I'm just going to pick a point, C. I'm going to go down 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if I'm going to do the same thing I did before, I'm going to use my, I'm not going to do the highlighter. I'm just going to have my 2 different colors. So red is like my in-between phase. Oopsie. Now, I do that again for each corner. Or I try to just recreate this. Like I can go, okay, so from point C, it's 1, 2, 3, 4, 5, 6 units to B. So B would be right there. And then A would be like up, or right 1 up 4, like there. If that's complicated, just pick a corner and go down 5 and right 5 again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom, 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 and boom. All right, first step is done. Translated, down 5, right 5. So it is now centered at the origin, it looks like. Okay, then we're going to dilate ABCD with a scale factor of 1/2. So our new shape is going to be half as big about the origin. So everything's going to zoom into the origin. It's going to be half the size, kind of zooming in. So how do we do that? Well, honestly, you measure like this distance here. You go, okay, well, look, from here to here, it's kind of like 2 blocks diagonally, right? What's half of 2 blocks diagonally? What's half this distance away? It would be 1 block diagonally. That is A prime. Same. 2 blocks diagonally, boom, boom. Half that would be 1 block diagonally. You're literally just going half the distance away from the center, from the origin. That was a little high. Whoa, too big. There you go. Closer. Now, this, excuse me, this might be a little bit uglier. Let's look at this line for a second. So from the origin to here, let's zoom in. There we go. From the origin to here, it's not exactly 1 or 2 blocks diagonally. I mean, can you find the halfway point in this line? You probably can. It's right here, right? Now, if just identifying it by this method doesn't work for you, you could also, there's other methods, like check this out. From here to here, you could go down to right, left 3. That's what it is, right? Okay, now what's half of that? What's half of down 2? Down 1. What's half of left 3? Left 1.5. That also takes you to that same location we had when we drew our line and did it the other way. So there's point B prime and C. Halfway, I mean, I'm just looking at this, it's down 2, so down 1 right there. Right there is where we want. and that is C prime. So that is our dilation. So now that's the whole sequence of transformations. We translated it, and I have my red thing. We then dilated it about the origin. I have this pink thing. The pink thing is our final. The red is just kind of like an in-between step. Okay, let's see if you can answer this. What are the coordinates for point D prime? Pause the video, do it. Honestly, you're probably done. It's 1, 1. D prime, right here. See, D prime. I even have it labeled. A prime, B prime, C prime, D prime. He's right here at 1, 1. How long is side D prime, C prime? I want you to figure out how long is this side right here. What is the length of this? I'm going to have you pause the video and try this on your own. When you're ready to continue, or if you get stuck, hit play and we'll go through it together. So there's two different ways of doing this. Both involve the same method. It's Pythagorean Theorem. You're going to find the missing side of a right triangle. So one method is you do Pythagorean Theorem on this little triangle. Let me get a nice black should work, I guess. So imagine this triangle right here. Well, we know this side is 2 big. We know this side is 0.5 big. That's half of a block. And I could do Pythagorean Theorem right here using 2, 0.5, and that. And we'd get our answer, which would be what? A squared plus B squared equals C squared, and 2 squared, this would be our right angle here, so that side is the hypotenuse. 2 squared plus 0.5 squared equals C squared, and calculator, 2 squared plus 0.5 squared equals 4.25 equals C squared. We would then square root both sides and square root that answer to get C equals 2.06 units. It's not like inches or miles or anything. So that is one way. You can just do Pythagorean Theorem straight from that little triangle right here. Okay, first off, 2.06 is the answer. Now, if that was hard for you and you had trouble, didn't know how big this was, you could have done Pythagorean Theorem here. We know all these measurements. We know this is 1, 2, 3, 4. We know this is 1, and we want to find this side. We could have done Pythagorean Theorem right there. A squared plus B squared equals C squared. 4 squared plus 1 squared equals C squared. I'm going quick because, well, we already did this. That's 17 equals C squared. I would square root both sides. C equals square root of 17. And we get 4.12. I'll keep the 3 for now. And you might be going, but that's not the same thing. Look, they're different. Yeah, but remember, if we took this and cut it in half, we did a dilation of scale factor of 1/2, right? If we took this 4.123 and cut it in half, divide by 2, now we got the same answer. So they're just different methods. You had choices, but it had to be Pythagorean Theorem. All right, some other little applications, little problem solvings. I know we've done a couple already, but there's more. Triangle XYZ has coordinates of that, and that. Triangle XYZ was then reflected across the y-axis and dilated with a scale factor of 3 about the origin. Which quadrant would you find point X prime? Okay, so in this problem, we only really care about x. I don't care about y and z. Which quadrant would you find point x? So, like, is it in here, 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 here? So, you know what? I'm not even going to put points y and z. I'm going to do just x. So x is at point 3, 4. 1, 2, 3, 1, 2, 3, 4. There is point x at 3, 4. This triangle was then reflected across the y-axis. Okay, so I'm going to reflect this across the y-axis. So he's 3 units away this way. So he's going to now become 3 units over here. Point x will be right there. So, boom. That way I can just keep track of which is the new and the old. So he reflected over there. He reflected across the y-axis, boom, and dilated with a scale factor of 3 about the origin. So now he's going to zoom out from the origin, 3 times farther away from the origin. So if you imagine from here, through this line, I'm just drawing a big line, okay, 3 times farther away. Well, he's going that way, right? 1, I'm just estimating 2, 3. So I'm imagining he'd be out there somewhere. Well, I don't actually have to figure out the exact point. I don't actually have to do that to figure out where he'll be. I can figure it out if you want me to. I mean, if that makes you happy. Right now, this has the coordinates of -3, 4. If we go 3 times farther away, instead of going 3 this way and 4 this way, 3 times farther would be 9 this way and 12 that way, which would be the point -9, 12. So if you wanted the point, there it is. I mean, again, that was a pretty good estimation. But the question is, which quadrant would you find the point x prime? He's right here. There's x prime. Do you know what quadrant this is? Does that word ring a bell in your brain from the past? Quadrant 1, 2, 3, 4. He's in quadrant 2. My teacher, or the way I remember this, is that the quadrants make a giant letter C. So 1, 2, 3, 4. I know a lot of students struggled and just misremembered that because it's been a while since you've had to think about it. So 1, 2, 3, 4. So this would be in quadrant 2. And yes, we do use Roman numerals. I don't know why, but we do. We use Roman numerals for these quadrants. So this is quadrant 2. So that wasn't so bad. That was a work smart, not hard. If I put in point y and point z and I did the whole reflection across the y-axis and then a scale factor of 3, I probably would have been really mad at myself if all I needed was where's x. So work smart, not hard. Letter B. Line LM with coordinates of 2, 5, and that, okay, has been translated using this rule. Okay, so it's translated, it's moved. Then the line is reflected across the x-axis to make this. What is the length of L double prime M double prime? Now, as I'm reading that, there's alarms going off in my brain saying, work smart, not hard. I could draw these 2 points, translate it, reflect it, and then I'm assuming do Pythagorean Theorem. I'm assuming that's the thing that's going to find the length of the line. Okay, so let's just start with our first line, like the original, the pre-image, this. So 2, 5. 1, 2, 1, 2, 3, 4, There is, what was that, point L, I think? 2, 5. And point M is -1, -1. There's M. So there's the line. Okay. It's been translated using this rule and then reflected across the x-axis. What is the length of the line after all these transformations? But you know what I'm thinking? If I translated this and then reflected it, is the length of the line going to change? Do I actually have to do those transformations? No, I don't. If I translated it, let me copy, paste. So it says we're going to go left, right 3, and down 1. That's what this, my x values go up by 3. That's right 3. My y values go down by 1. And then I would take this and reflect it across the y-axis. Now, I can't do that with the magic of notability. I would have to just do it by hand. But I don't actually have to do it. There's m double prime and 1. I'm actually, what I'm doing is I'm counting boxes. So this was 2 here. It's 2 here. I'm counting this. 1, 2, 3, 4. 1, 2, 3, 4. L double prime. There. So this is the same length as this, and all 3 of these are the same length because no dilation happened. So by working smart, I could have just said, you know what, if I just find the length of this line right here using Pythagorean theorem, I know it's going to be the same in the end. But I wanted to show you the process of also doing the transformations. Like, I did the translation, I did the reflection, but I didn't have to. Now, as far as doing the Pythagorean theorem, I would encourage you, if you'd like to pause the video quickly and try this on your own, hone those skills and make sure you still got it, fine. If not, I'm doing it now. First thing I'm going to do is I'm going to draw a right triangle. That is 3 units. That is 1, 2, 3, 4, 5, 6 units. Let me double check that. 1, 2, 3, 4, 5, 6. Okay, we're good. And then I Pythagorean theorem that. The missing side is my hypotenuse. So 6 squared plus 3 squared equals c squared. That's 36 and 9 is going to be 45, but double check it. Told you. 45 equals c squared. I'm going to square root both sides, and c equals 6 point something. 6.71. Rounding to the nearest hundredths, the 8 would make the 0 round up to a 1. So that would be the length of the line. It's the length of all 3 lines. The pre-image, the first image, the second image. Work smart, not hard. That's the advantage of kind of being smart and thinking through a problem, is you can make those kind of decisions on your own. Letter C. Here's one for you to try completely on your own. Quadrilateral PQRS is reflected across the x-axis, then dilated with a scale factor of r equals 3. If PQRS has a perimeter of 22 and an area of 30, what are the perimeter and area of the new image P prime, Q prime, R prime, S prime? Okay, my only hint before I send you off on your own is make a sketch, draw some pictures, okay? Go ahead and pause the video, try it. See how far you can get before you quit, or see if you can get the whole way to the end. When you're ready to continue, hit play, and we'll go through it together. Okay, so the sketch. I'm going to just, I don't know where these things are. I'm just going to draw a quadrilateral. So quadrilateral is like a rectangle thing. It's reflected across the x-axis. Okay, so it goes down here. And then dilated with a scale factor of 3. So it's going to become 3 times as big. So that's twice as big. There, we'll call that 3 times as big. It doesn't say where the center of the dilation is, but honestly, we don't really need it either. I'm just getting myself a sketch so I know what's going on. Okay, if PQRS, the original guy, has a perimeter of 22 and an area of 30, what are the perimeter and area of the new guy? All right, so things we know. We know that each side of this is now 3 times as big, right? So like this side is 3 times bigger than this side. That means we can easily find the perimeter, because the perimeter would literally just be 3 times as big. 60, there's the answer. 22 times 3. It is 3 times as big. Each side is 3 times as big. The perimeter is 66 centimeters. Area. The area is not 90. The area is not just 3 times as big. Remember, it's 3 times as big this way and this way. So I have a question for you. Could you think of a rectangle? Could you think of dimensions of a rectangle that actually have this perimeter and area? So I'm thinking like, 5 and 6 gives me the right area, but not the right perimeter. Actually I lied. It does. 5, 6, 5, 6, that would be 22. So, okay, let's use that. If that got 3 times as big, this would be 18 and this would be 15. Right? 3 times as big, 3 times as big. And then, if we did 15 plus, this is the perimeter part. There's the perimeter of 66. 15 plus 18 plus 15 plus 18. Okay? Area, length times width. It's not 90. It's 270. It's not 3 times as big, it's 9 times as big. It's 3 times as big this way and 3 times as big this way. That's 9 times as big. Squared. Okay, that takes a little bit of problem solving. I had to try some stuff. I came up with side legs that actually made this work out. You can do that. That's simplifying the problem. That's giving yourself additional information. And then when I made it 3 times as big, I could then easily find my perimeter and area. And I encourage you to try stuff like that as well. Summary. How does a sequence of transformations make congruent figures? And how do they make similar figures? Think about your answer. This is kind of just a summary of the lesson, summary of the essential question. So pause the video, think about it, and we'll get to it here in a second. So a sequence of transformation can make congruent figures as long as you're only doing a reflection, a translation, or a rotation, in some combination of those. They will make similar figures if you do a dilation with some combination of the other ones. So similar figures because a dilation happened. Congruent, I hate when it does that. Congruent figures, because these are all the same length. Only a translation and a reflection happened. They are congruent. So if a dilation happened, if I actually drew the triangle, these would be similar because a dilation happened. Okay? That's how you can tell. If a dilation happened, they are similar. If only a rotation, reflection, and translation happened, they are congruent. Thank you so much for watching this lesson on sequence of transformations. Until next time, toodles.